These were the options it gave us on ICs. Now we could have done this, guys, but notice the AND gate they want us to use. What AND gate do they want us to use? 7411. Okay. But when we look at our schematic, it calls for a 2-input AND gate. What's the 7411? Look it up in the front of your textbook would be the fastest way to see it. $7411. What's the 7411? It's a 3-input AND gate. What do we need? We need a 2-input. So how could I use a 3-input AND gate for a 2-input AND gate? Anybody got any ideas? Well, we could, because an open input of a basic gate is usually assumed as a high, right? So we could leave it floating, but any good engineer would never leave an input floating. That's like Marines never leave a man behind, right? So a good engineer would never ever leave all inputs floating. So we got two options. We could come over here and I could do this. So that would be okay, right? You understand that? Or I could come over here and I could do this. I could connect this up to 5 volts and do that. Now, which one's best? Well, this right here would count as 2 loads. So it depends on what we're loading this with, right? You understand? This right here would count as 1 load. I mean, each one of these would be a load, but this one input, whatever gate is feeding this would be feeding 2 loads. Now, rule of thumb, if you don't know, rule of thumb is that most TTL gates can drive 10 loads, like loads. So if you're mixing 74 LS and 7400s, you need to look it up on the data sheet. But normally, if LS is driving an LS, then normally the rule of thumb is 10 loads. But we're not going to do that. But this is one way we could do it, right? So I shifted over, even though the lab don't call for it, so I wouldn't have to do stuff like that. I shifted over to a 7408. What's a 7408? Look that up in front of your data book. So it's 2-input AND gate. So this is the guy we're using. So let me tell you what pins I used. I've already wired it up for y'all. So let me tell you what pins I'm using. Oh, let me bring the lab back up. Where's that at? Where's that at? Where's that at? Oh, it's right there. Yeah, NOR's wired up the same. It's exactly the same circuit. Well, sorta. It's just we're feeding the inputs through the AND gates now. Got 3 switches hooked up now. We got one called enable, and then we got our S and R's. So my S, I have hooked up to, still have it using switch 7. That's pin 2. In my R, I'm using, oops, I'm using pin 5. My enable, I'm using switch 5. I have it connected to pin 1 and pin 4. And my output of the A gate, which you use 1 through 3, so pin 3 would be connected to this guy, and then this would be 4, 5, 6. So pin 6 is connected to that guy. So guys, tell me how this thing's gonna work. Okay, so let's so we got a truth table we got to fill in, right? So the first one would be just a random state, right? You understand that? Let me find my camera. Of course, ours was already on, so it can't. This one comes up to be reset every time. So I'll turn power off and turn it back on. Oh, it came up set that time because of the NAND gates. The NAND gates are different. But notice, last time it came up what? It came up reset all the time. What's it coming up now? It's coming up set all the time because of the NAND gates. I mean the AND gates, I'm sorry. So that's an ambiguous state, so we don't know what it is, right? All we know it's going to be what? Not yet. So here comes the clock. So right now the clock, so my clock is switch 5. It's not going to do anything because it's what? Both the inputs are low. It's latched, right? So the clock doesn't do anything about it being latched. Or not the clock, the enable input. So what we're going to do next, I'm going to bring the set to a 1. Let's clear it first so we can see this happen. Okay. So let's say we start from here. I'm going to bring the set to a 1. Why didn't it set? Because it's not enabled, right? You understand? Here it comes. I'm going to enable it. So here's switch 5. So as soon as I enable it, it did what? It changed. Now I can come over here on these sets and resets over here. They don't mean anything. Why don't they mean anything? Because it's disabled. Okay, you see that? Yes or no? Okay, I'm going to bring the reset. What's next? It says I need to bring the reset 1. By the way, let's do the Q and the not Q each time, right? So this is the Q. This is the not Q. Huh? The 1 is the Q, just like a while ago, and 0 is the not Q. So we started off and we said it was latched, right? You understand? And then from then on, we're controlling it. Everybody understand that? Okay, so I'm going to bring the set to a 1. That's what it says for next, right? No, I'm going to put 2 zeros and I'm going to clock it, and what did it do? It stayed what? It stayed set, right? But now we're controlling it. The first one we don't know. After that, we're controlling it, right? So it stayed a 1. Okay, now what does it want me to do? Bring the set to a 1. Bring the reset to a 1. Why didn't it reset? Enable. Okay, so as soon as I enable it, it resets, right? Now I'm going to bring this down. Now I can come over here and flip these things all over the place. Means nothing, right? Because why? It's not enabled. Yeah. Okay. Bring this back to a 0. Flip. Give it a enable it. It stays what? Latched, right? Everybody okay? Huh? Yeah. Both zeros. So set and resets both zeros. So we're on step 1, 2, 3, 4, 5. Just did step 5. Then step 6, I'm supposed to do what? Bring both of them high. Okay, sorry, I had to clock up. Bring both of them high. And I enable it, both Q and not Q goes low. But look, when I bring it down, it's going to take some state, right? Y'all understand that? Yes or no? Oh, came up set that time. Came up reset that time. Came up reset that time. Came up reset that time. Oh, came up set that time. I flipped it off. So see, now it came up set. So that's why if we put 2 1s, they call that an ambiguous state. Now, why do they call it an ambiguous state? Because there's no guarantee how it's going to come up when you bring it out of that state, right? So all I'm doing is flipping the enable. Oh, see, so there it came up set, there it came up, I'm sorry, there it came up set, there it came up reset, 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 set, reset, 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 set. So see what I'm talking about? So they call that one the ambiguous state, because when we bring it out of that situation, the latch comes up, we don't know, right? Okay, so you see what we did. What did we do? We added an enable to this, so that would be pretty good for me to have a latch. By the way, this is a latch called this is a 7475 right here, same circuit. Then we're going to add what to this? What's the next circuit we're going? This guy right here, an edge trigger circuit. Does it tell us to build this? Oh yeah, step 4. This is going to be hard to see though. We'll look a scope up to this. Oh, God, So we'll just look at this, and we'll have to look at it with a scope, like we did the other day. So I'm gonna come over here and use the clock output of my trainer, and then I'm gonna bring this into a one input of my 7408. Okay, so I'm bringing it into pin 8. Are we okay there? And then I'm also going to take this same input, and I'm going to jump it over to pin 1 on my 7404. And then I'm just going to start jumping this, right? So I'm going to go 2. I'm going to go 2 to 3. And then I'm going to go 4 to 5. Two to 3, 4 to 5, 2 to 3, 4 to 5, and then I'm going to take 6, 1, 2, 3, 4, 5, 6 over to 13, That gives us 3. Then I'm going to take 7 here. That gives us 4 here to here. Yeah, so I brought my, so here's my clock coming into my AND gate. So I'm over here on pin 8 on my AND gate. Nope, sorry. It switches around, right? 1, 2, 3. So on pin 8, 9, 10 on my AND gate. That's an input, right? On the AND gate, 10's an input. So I'm bringing my AND gate over, I'm bringing my clock over to pin 10, and then I'm also bringing it over to pin 1 of the 7400. Now the output of that uses pin 1 is going to be pin 2. So I have 2 jump to 3. Then I have 3 jump to 4, right? I have 2 jump to 3. I have 3 jump to 4. And then I take, instead of going from 6 to 7, I can't go for 6 to 7 because that's ground. So I've got it running over to pin 13. So it'd be 1, 2, 3. That would be, how many would that be? Okay. So what we're doing is we're doing this circuit right here, but instead of using 3, we could use 3. So I'm doing this circuit right here. So here's my 7408. I'm not going to use pins. So we've used the left hand side. We've used that for the other circuit. So I've jumped over to the other side, right? Y'all understand? Yes. Y'all understand? Yes or no? So what pins does that make available right here? So what's the pins for the first one on the bottom right on the right hand side on the 7408? Yeah. What's available? Pin 8 is an output, right? Okay. I'm using inputs right now. So what's the input? I'm using inputs right now. So we're on this side over here. Okay. So I'm bringing my clock into 10. Okay. Now not only does 10, so I'm bringing my clock into 10 down here. Okay. And then I'm working on this circuit right here. Okay, you understand that? I got a 74. So what I've done is I've taken my clock input and I've connected it back over to pin 1. So this would be what? 2. And 2 is going to jump to what? 3, right? And 3 is going to jump to 4, right? Okay, 4 is going to jump to 5. We got to jump. So 1, I'm jumping what? 2 to 3, 4 to 5, 5 to what? So 1, 2, 3. Okay, so I've got this guy right here. Okay, so that would be 1. That would be what? 2. That would be 3. That would be 4. That would be 5. 6. What does 6 have to jump to? I could have went to. I went up to. Uh, I'm coming down the other side because I'm running. So I went up to 13. right? Okay. Are we okay? Yeah. Oops. Are y'all with me? So I'm coming down this line right here, right? And I'm using one. What's the output of one? Two. And then I'm going to do what? Jump two to what? Three. And I'm going to do what? I'm going to jump four to five, right? Okay. And then, oh, I'm sorry. I knew something was wrong. Thank you. So I'm going to come out. I just said if y'all was paying attention. So this is, yeah, this is four. This would be five. Six, I've got going to 13. No, y'all didn't hear what I said. I said the scope is going to have such a hard time seeing this many. We're going to add another propagation delay. Yeah, we're going five. We're going to go five. Okay, and this right here would be 12, right? And then this right here would be 11, and then this right here would be what? 10. Are we okay? Yes or no? No, it's okay. We'll just do it like that. I could have left three, but I just know from experience our scopes has a problem picking up that edge, and what we want to do is see it really well, right? You understand that? So we're just not acknowledging it. It's there, but this scope right here is a 25 megahertz scope, and and that's the bandwidth. The bandwidth is what the scope guarantees, the frequency it guarantees to show you at least 70.7% of what's there. Well, the problem is that we're looking at a fall time. So even though I'm looking at let's say 100 hertz, we're talking about the frequency of how fast this thing is falling, right? You understand? So if this thing takes 10 nanoseconds to fall or less, then we're talking about a real high rate that this scope just can't watch, just can't read. And it's going to have a hard time with this, but take my word for it, it is pulsing all the way to ground or to 0 volts. It's just that the scope it's already on its way up before the scope can get it down there. Right. So 10 will go back to 9, and I'll hook my scope on 8 so we can look at that. So what I'll do on the scope is I'll look at the clock coming in, and then I'll look at the output, and we'll see which edge this thing detects. Now this is an AND gate, so we should expect it to find the rising edge, right? Or gates would find the what? The falling edge. Yeah, and if we turn it up too high, it'll get spread out. You can't see it on the screen anymore. Yeah. We could probably spread it out a little bit. So this is what we're looking at right there. No, most of the scopes that we have a 100 megahertz scope in there, but I'm not going to lug it out. We got 200 megahertz scopes. We got one digital 100 megahertz scope that we got from a grant, and then we got our logic analyzer slash oscilloscope. It's a 100 megahertz scope. It would probably do better, but there's really no need to because we can see it working here. But I'm going to slow this down, and so we should see a blue pulse for every rising edge, right? It's hard to see because the scope's having all kind of problems now. But you notice every time I see a pulse, it's on a what? It's on a rising edge. What's that? Right. If instead of using yeah, in an OR gate, you're right. We would get a rising edge detector. So what we have to do, and so what they do is they change the symbols a little bit. Yeah, falling edge detector. Did I say so? So if I come over here and like I look at this 7476, what we'll see is that we pick up another signal right here. So see the way this pin is labeled. So you'll see the triangle in there. Anytime you see the triangle, it means that's edge triggered. If you see the bubble, it means it's edge triggered on the falling edge. If it don't have a bubble, it means it's edge triggered on the rising edge. Now we know the circuit that's inside there to cause that to happen, right? Normally these signals they don't call them enables, they call them. Can you see what it says? CLK. What do you think that stands for? Clock. Yeah, clock. Yeah, we got two of these guys in there. So remember, these are integrated circuits, and if there's enough space inside there, they put multiple units in there. So what we're looking at is there's actually two of these flip flops in there. These are JK flip flops. There's two of them in there. So notice these are latches or flip flops. There's Q. So they got one called Q1 and not Q1 because they're calling this latch, they're calling this guy or this flip flop, they're calling it the number one flip flop, right? You understand? This guy right here is the number two flip flop. So how do they label the Qs on there? They call it Q2 and not Q2. And then we got a J input we haven't looked at yet. We got a J2, we got a K2 somewhere. Oh, J2, K2, so there's K2 because these are JK flip flops. So we got two inputs, and that's why they're called JK flip flops because one of the control inputs is called what? J, and the other one's called what? K. And then we got a clock. So J and K means nothing unless you have a what? What clock though? You got to have a falling edge. A falling edge. So this guy here would only switch on a what? On a falling edge. So that's what they're telling us right here. So it's saying, okay, for this thing to work, I got to have a clock pulse. So this is a symbol that you'll see added to this. Now, if I go back and look at another latch, if I go back and look at where's Blackboard at? Where's it at? Where's it at? Where's it at? It's gone. It's still logged in. It'll bring it back up. But if I go back and look at like a 7475, which we looked at the other night, it don't have the clock symbol. So what we call those latches is we call those level triggered. Y'all understand? So we got level triggered latches. Those are going to need to look for a what? A high or a low. An edge triggered flip flopper latch is going to look for a what? An edge. Y'all understand the difference? Well, one of them's looking for a high or a low. One's looking for an edge. So the 7476 was looking for a what? An edge. Let's look at some of these flip flops in here. I need to close some of these out. We're not looking at this one anymore. We're not looking at this anymore. And this is about, guys, where we're gonna move on and don't do all these circuits because from now on, all these circuits are integrated. So these other latches and these other flip-flops, you will never see those wired using individual components. You will buy them, right? You understand? So a JK flip-flop is actually on the very back. So look at figure 15-5. This is a JK flip-flop. Now, how many of you want to build that circuit? How often do you think a JK flip-flop's used? It's used all the time. So how long did it take them to integrate this into a single wafer? Not very long, right? You understand? So we're not going to wire these things up because you'll never see them wired up. All we'll do is what? We'll figure out how they work. All we know, okay, if I understand the input and I understand the outputs, I really don't need to know what circuitry. Can you imagine the circuitry just for that NAND gate right there? We draw on the circuits of an AND gate, right? Y'all understand that? And then you take that and we have the NOR gates, we have the AND gates. We got this don't even have the edge trigger circuit, so this is still missing some stuff. So this uses an enable. It's not even edge triggered. The 7476 is edge triggered. So this little circuit that I've got right here would also be included inside that integrated circuit, right? You understand? But the problem is that if I wanted a JK flip flop, I wouldn't build the JK flip flop. I would do what? I'd buy it, right? So let's look at some of these flip flops. We have just the data sheets we have on the blackboard. Usually if it's got a 7 in there somewhere, it's usually a flip-flop. I mean, not on here, right over here on the end. So if it's a 74, 75, a 74, 74, a 74, 175, a 74, 174, just about every one of those guys are going to be some type of flip-flop or some type of latch. So here's a 74, 74. So let's just look at this. So this says it's what? It says it's a D-type positive edge triggered flip-flop. This is the makeup of it, but it's not quite right. They show this as a NAND gate. They got to have that edge trigger on their circuit on there, right? Y'all understand that? So we looked at a D flip-flop. We drew that thing up. What did we say about a D flip-flop? Y'all remember? A D latch. So all they do on a D latch, of course, they add the enable to it. So all they do on the D latch is they'll come over here, and we talked about this last class. Y'all remember? How do I remember this stuff and y'all don't remember it? Oh, yeah, how do I remember we talked about it when I'm teaching all these different classes? So what we do is we just take all we do is take an SR latch. I'm just going to draw it like this. Y'all understand how that works, right? Q and not Q. And then we add an enable to it. Okay. And then what I'm going to do is I'm going to bring in the S. I'm going to come down here. I'm going to put an inverter and use that to bring in the R. Then we come up here. Now the signal is changed. Now I have something called D, which represents this circuit right there. And then I'm going to put an E right here. And then I have a Q, and then I have a not Q. And we call this a D latch, or they call it a D flip-flop. I refer to it as a latch. We can make it flip-flop. I'll show you how we can make it flip-flop. So that's all there is to it. But if this goes to a 1, and I enable this thing, what's it going to do? Yeah, so this will be a 1, this will be a 0, so it's going to set. Well, what if I leave it enabled? And then I go right here, this will be a 0, then it's going to do what? It's going to reset. If this goes to a 1, it's going to set. If this goes to a 0, right, you understand it's going to reset. So as long as the enable is true, D follows, I got too many L's. Q follows D. Now what about if E is false? It's latch. And that's a D flip-flop if it's level triggered. So if we look at a 7475, it is a level triggered D flip-flop. As long as that E is high, the Q will follow. Whatever D does, the Q follows it. But if the E goes false, it latches. Whatever's on the D input at that instant is what it latches. Now the 7474 is an edge trigger. So it's not going to follow D. It's only going to take the state of D on the edge, right? You understand? The 7475 is what we call a level triggered latch. So a level trigger latch, as long as that E is true, this sucker, that the Q out, the D input is going to pass right through. So let's look at the symbol of a 7475. So let me find 7475. This is the same one we looked at the other night. It is a what? It's a bistable latch. Then I start reading. It says, these latches are ideally suited for use as temporary storage for binary information between processing units. An input-output or indicator unit. Information presented at the D input is transferred to the Q output when the enable is what? High. So whatever's on the D goes to the Q. And the Q output will follow the data input as long as the enable remains what? High. When the enable goes low, the information that was present at the data input at the time the transition occurs is retained in the Q output until the enable permits it to go high. So that's a beautiful explanation. I couldn't have wrote that any better. I mean, that's just laid out exactly what this thing does. But we call this guy here a level triggered latch, right? You understand? Because as long as it's enabled, the what? The Q will follow D. Now, it's kind of strange in that how many enables do you see? So the enables they call C. How many latches do we have in there? We have 4 of them. They call them 1, they call them 2, they call them 3, and they call them 4. So here's latch 1. It's between 1, 2. So the D input is on what? Pin 3. I'm sorry. The D input is on pin 1. The Q output, the not Q's. Yeah, I need to put my glasses on. The D input is on pin 2. The not Q's on what? Pin 1. The Q's on pin 16. And where's the enable? Well, the enable's down here on 13. So this guy, that's 1C, right? You understand? So what happens here is that I guess they run out of pins. So pin 4 is going to enable flip-flop or latches what? 3 and 4. And pin 5 is going to enable latch flip-flops what? 1 and 2. So what's that? I'm sorry, pin 13. I'm getting tired. Huh? So you see there's 4 of them in there, right? You understand, but these are level triggered. These are level triggered. And that explanation right there is beautiful. By the way, these are international symbols. On the international symbols, on the IEC, the International Electrotechnical Commission. Oh, yeah. We just, yeah. So let's see if I don't know. And you got a, I see. So this is an international symbol. Okay. And notice what they do for low active outputs. They put a what? Put that triangle thing on there. I don't like these things. Huh? So if they did a 2-input AND, it would be a square, and it would have the AND in there, the like on a keyboard, and then it would come straight out if it's an AND. If it was an AND, it would not. It would have that triangle on there. So international symbols, all your basic gates are drawn in squares. Well, it's an international symbol. So it's an international symbol. Y'all know what the symbol of a resistor is? It's just a square. I mean, it's just a little rectangle, but it's a tiny rectangle. Well, not really. If it's and it's also the symbol of a relay coil, but the relay coil has two little slashes in it, so that would be a coil. So they don't draw a coil as a circle like they draw it as a rectangle, but it's got two little slashes in it. Well, yeah, you say I'm going to stick to the U.S. standard, but you know a lot of this stuff is international. So, but you got access to it, right? So, I mean, you could look it up and get these international symbols. What's an and? What's an or? So anything you get from Siemens is going to be what? They're going to be IEC symbols. So all the diagrams and everything you get from Siemens are going to be IEC because they're a German company, right? So Festo, if we started looking at the prints on the Festo line, they're using what? International symbols because they're a German company. So what we're saying is that, you know, if you work in a company like Mercedes or a lot of these companies, these tier 1 companies, they're going to use what? They're not going to use the American symbols. They're going to use what? Or they're not going to use the IEEE symbols. They're going to use the what? Yeah. Well, they're so, you know, yes, I like our symbols better, but you know, I think in Chinese they start on the right hand side and they write vertical, and they start on the right and come this way with their characters. Uh, we So then we come up and we look at it. So this is a D latch, but it's what we call an edge trigger, and then we go back and look at the 7470. Dang it! I keep hitting my tabs, and what am I doing when I slide? I'm hitting the exit. Yeah, I do that all the time. So this is where, like I said, we'll come back and look at some of these flip flops next week. Y'all go ahead and work on y'all's labs for the next hour.